Okay, this is the second session for the methods for simulation in stochastic processes in systems biology. Today, I'm going to talk about the process of the telegraphic wave. Okay, so this process, in the last meeting, we talked about the single step process that corresponds to a system of two states when you have a given transition rate, or also called propensity function. And you can solve the system using the associated master equation, finding the distributions of probabilities in each state and the distribution of first pass times. So here, the system is a little more complex. So we'll still have two states, but now we have the possibility of coming back. So you have the transition from 0 to 1, or at a rate lambda, and the transition to 1 to 0 at a rate lambda 2. These lambdas can be also different, but for starting, we can like take them the same. So a particular example of a trajectory you can find in this kind of processes is something like this. So you start here from the state 0, and you jump to the state 1, and then you do a random transition again from 1 to 0. Okay, so to model this system, we can propose this master equation. So we have like the fluxes of the probability, dp dt and dp minus 1. So here you can put any name to the states. So in this first part, I have 0 and 1. Here I have 1 and minus 1. You can put the names, for instance, A, B, state X and Y, etc. You can put any name you want. It doesn't matter. So let's call the first state 1 and the second state minus 1 for the notation. So you have here two fluxes. Let's say the first state is this one. And you have one incoming flux and one upcoming flux here. Yes, so the derivative of that state as a function of time is the incoming flux. In this case, is lambda, that is the rate, times the probability of this state. We can call it P1. In this form, in this system of equation is -1, but it's the same. And so this flux is this one, and this flux that is upcoming is negative because going out. So the same, and it's times the probability of this box. And the same for the other, we have something like this in the end. One positive, that is the incoming flux, that is this, and one negative, that is the outcoming flux, that is this. So we can solve the system. We can like say that the system is a linear one, such as you can represent it as a vector P1, P minus 1 is a matrix with these elements, -1, minus lambda, lambda, minus lambda, and lambda. And this system can be solved using matrix exponential methods. Okay. So one example of the uses of this system can be, for instance, found here, where you have the possibility of do fluctuations on your environment. So your environment can take approximately two states, high and low. For instance, can be high amount of nutrients, low amount of nutrients, can be antibiotic, non-antibiotic, or a treatment, no treatment, and you can fluctuate them using this kind of system, like randomly. Other applications can be the switching between two states. For instance, you have here two possible phenotypic states, let's say blue and yellow, can be like the expression of a given gene, a given enzyme. And if the possibility of switching from one phenotype to the other phenotype in a random way, you can, as a first approximation, model them using a telegraphic wave. With in this case, the rates can be K plus and K minus, can be one greater than the other, or they can be also symmetric. One example can be like the phage, lambda phage lysogenic and lytic states, bacterial persistence, and other kind of metastable systems like the open-like and the GAL system. Okay, we start with the master equation. The solution, as I told you, can be found using the exponential of this matrix. And if we have these initial conditions, like for instance, we start with probability 1 and at the state 1 and probability 0 at the state minus 1, you obtain these expressions. These are like the analytical formulas for each probability. Okay, so you from these probabilities, if you give some number to the each state, for instance, -1 to one state and 1 to the other state, you can estimate the mean over time, the second order moment, that is the expected value of the value squared, and from that one we can estimate the variance. Okay, so how can we simulate them? Okay, so the idea is the following. First, always you have to define the initial condition. Let's say we start here in the state 0 or the state lower, the lower state. And now we know how to obtain exponential times using the Gillespie formula. So we calculate the next time to reaction, and we have two options. And we define the maximal time, or the time when the simulation finish. So one option is like there's no reactions until the end of the simulation. So you essentially do nothing and export the data. However, if there are one or more reactions between this time, you perform the reactions while the time is less than the maximum time. So you can, so you calculate the first reaction, do the reaction, then you jump, redo the reaction, and so on. And then when you finish, you can export data, or you can finish your simulation, and so on. Okay. So an activity simulate 1,000 trajectories of the telegraphic wave using the Gillespie algorithm and obtain the moments of the trajectories and compare it with the analytical solutions. Okay, we have here our notebook as always. And here I have my reference. Okay, so the first thing we can do is define our function. So what's the idea? For instance, if I want to export data, I have to simulate the data until the next time that I'm exporting the data. So this Tmax is not always the final time of the simulation, but can be also like some times when I do or when I export the data for plotting trajectories. In this case, this is what I did here. So I export data here every 0.01 units of time. So I have to stop the simulation every time I export the data. Okay, so we define the function. So my function can be evolved that is going to depend on. So for simplicity, let's assume that the the transition rates are symmetric. So let's call it lamp, the transition rate, the maximum time, and the state, the initial state of the system. So what do we do here? Calculate the first time of reaction. The time of reaction can be using the Gillespie formula, 1 over the rate times the natural logarithm of a random number from 0 to 1. Okay, and then we check if my time to reaction is greater than my final time. So other thing is I can start the time from 0 because I need a timer for the reaction. And if my time to reaction is greater than Tmax, do nothing, no? Return the same state. Else, so we have to do the reactions. As most reactions I have to do until I finish or until I do or I end the simulation. Okay, so while t, in this case, this variable t is gonna track the time while t is less than t max. Or yes, so I want like every time I'm gonna jump my time the time that each reaction spent, right? So I have to check while my time plus the next reaction time is greater than my goal time. Okay, so I have like to sum up the new reaction time. So it's T plus the next reaction time that for us is gonna be TR. So while this is less than T max, do their reactions. So what are the reactions here? The reactions are if my state is 1, jump to 0, and if my state is 0, jump to 1. Okay. So if my state is 0, is equal to 1, and otherwise is equal to 0, and that's it, no? Return S. Okay, that's the basic algorithm. So we can implement it using this function here. So what is algorithm consistent? So we have sorry, here I have to add the tau, no? So t is gonna increase by an amount of tr. And when t plus the next tr, I have to also to calculate tr every time I do the reaction. So I calculate the next tr for the next reaction. And if this t plus this tr is greater than t max, I finish the reaction, I finish the simulation, and return this value. Okay. So we start with my time. I'm gonna export data every 0.01 units of time. And I start the state in 0. And I'm gonna save the data in this kind of arrays where we have that they are, each of them are elements uh, of arrays of 2 elements. The first element is gonna be the time, and the second element is gonna be the state. Lambda here can be 10, and my maximum time is gonna be 1. So what's this? What's the algorithm? So let's say I'm gonna evolve this time in units of delta t. So what I'm doing here is, let's say this is my telegraphic wave. So I propose a delta t that is the time of exporting data. So I have multiple of them here, and I evolve the system at time delta t, for instance, from here to here, and then I export the data. Then I evolve to the next delta t, and so on. Okay. So I evolve the system. So the lambda is going to be lambda. The maximum time is going to be et, 0.01. And my state is going to be the same state, like just in the beginning of the interval. And the output is the state S. So is my new state is going to be like the output of this. So as you see, there's the possibility that you're going to have multiple transitions, but since you cannot see them uh, during this time interval, so it doesn't matter very much to you. Okay, we evolve the time t and save the date. Mm, What's the problem? got stuck here. Seems that it was a problem of the computer. Okay, we save the data in this data frame and we plot. Okay, so if we see the system here of this data frame, it corresponds to the state of the environment at a particular time. For instance, we can also do a scatter plot using this, and you see like the point of the each time instant. Yeah, so each point corresponds to the data set. So you can decrease, for instance, also the accuracy, but you're still gonna have similar statistics. So here, like the accuracy of this trajectory is 0.1. If you want to do it with less accuracy, so like the limit is the one you want. In this case, you have the same. If you have less or higher accuracy. Okay, so the idea is like to simulate 1,000 trajectories and estimate the mean and the moments overall. So we can do this for 1,000 cells. So let's say we're gonna simulate 1,000. So we can do for A in range 1,000, so 1,000 times. We can do this. And my data can be the array or the data frame of all the elements or all the uh, trajectories of all the cells. So here I have to add a new column that is the column for let's call this n of this cell now because we have 1,000 cells. So we save cell in one column, time in another column, and the state in another column. Okay. Probably 1,000. This DT is too big, too small. And then we save it in a data frame. Okay. So the difference with the previous data frame is that this has another column. So let's call this column cell. We can see the DF here. So we have 1,000 cells from 0 to 999. The time in with this resolution and the state of our wave. How can I calculate the moments? So I have here the trick. Okay, so we can check the time. Let's call this TF cells now. So we have here the time. If we do TF cells dot time dot unique, So this function is going to give you an array of all the times that are at least once in the data frame. So you have 0 0.01, 0 0.02, 0 0.03, 0 0.04, and so on until 10. So for time, in this array, I select as DFT a new data frame. The data frame which has this date, the time of this data frame is equal to time. For instance, if I want time equal to 0 0.01, I have all the cells, cell 0, cell 1, cell 2, all of them at time 0 0.01. So the states of all cells, 0, 0, 1, etc. And I can calculate the mean of this state. So I have assigned this state two numbers, 0 or 1, but can be -1 or 1, can be 2, can be whatever. But arbitrarily, I select here 0 and 1. So each state can be this 1 and 0 and uh, anything you want. So I calculate the mean and I save the time in this array called here. Or we can do something similar to what we have done here. Or we can do, for instance, again, add an array of data and save the time in one and the mean in the other column. And then save it as a data frame. The first column is going to be time. And the second column is going to be the mean state. Okay, we can even do the second order moment. For instance, the variance. We can save the variance as like simply the variance using the function mp_var of this array, and we save it as a var. And we have again our DF has the mean and the variance over time. And we can plot the time and the mean state, for instance. And we have something like this. What do we expect? So from the theory, we have like the probability of the first state follows this, and the probability of the second state follows this. Okay, so let me do this. Okay, so we have like the probability of the first state is gonna follow 1 plus e to the -2 lambda times the time over 2. So just at time equal to 0 is y is 1, and the other one is the same but negative the exponential. So the mean is going to be simply the first state 0 times this probability over 2. So this guy is 0 because everything times 0 is 0, and 1 times this guy, no? So it's simply 1 minus e to the minus 2 lambda t over 2. And so we can compare it with my function. This function is 1 minus exponential of minus lambda times the time over 2. Okay, so you have here the comparison. Mm. It's 2 times, no? Yeah, now you have more accuracy, like in the beginning at least. You can increase this to 10,000. Let's see if it doesn't waste too much time. And get a higher resolution. Okay. Okay, great. So the next, okay, as a homework, I will like to see what happens if my times are not exponentially distributed. So what you can do is here, for instance, instead of using this Gillespie thing, we can use any other distribution. For instance, you can be, let's say, normal distribution. With a given mean, for instance, 1, and a given standard deviation. Not that very high because we don't want this to be negative, no? And you can use any other kind of statistic, not always the exponential. Uh, it's positive. Uh, okay, the thing okay, here is a little bit different because here I'm using the Markov property. Mm, so in this case, I have to save the time to reaction and subtracting the new reaction. But I think we can explore this non-Markovian statistics later for next session. Okay, so in this last part of the session, let me talk about the Poisson process. So the Poisson process is like um little more complex process consistent on the occurrence of different uh, transitions that occurs each of them at a given rate. For instance, it's a counting process from 0 to a given number. So you start from 0 And then at the rate lambda, you jump to 1. Once in 1, you jump to 2 at a given rate, and jump to 3, and so on at a given rate. So this can be associated to the production of proteins from 0 to time 0 to a given time. That you start to count the number of proteins you're producing. So given this state, as you said, you can see here the number of states is infinite because it goes to 0 and doesn't have any like upper boundary. And you can propose the master equation. So the state 0 has an flux out at the rate lambda times p0. The box 1 has an influx of rate lambda times p0, and it's positive, and flux out with the state with value lambda times p1, and so on. Overall, any particular state n has an incoming flux lambda and outgoing flux minus lambda. So we can solve this master equation. So this has a little more complexity than the previous one because the system has multiple states. So what we do here is like the first state can be solved is simply an exponential function of time. And then knowing that this one, that this guy is exponential, you can solve this thing using the convolution of integrals. I won't stop like explaining how to do it, but I'm gonna tell you like this is the solution overall. Like if you know that solution of Pn minus 1 of time, the solution of Pn is the convolution of Pn minus 1 with this exponential function from minus infinity to t. And the solution overall, for instance, is this function here. Okay, so the convolution of an exponential with this other exponential is this. And if you do it n times, you're going to get this function that is called the Poisson distribution. And it gives you that at a given time, t, and a given rate lambda, what is the probability of having n steps done, or n proteins produced, or n steps overall. So we can calculate the mean and the variance using this distribution. So how can we calculate? You know that the mean is the mean value. Now these variables are discrete. So what you do is summing up the state n times this distribution. So it won't show, but you can like at your home check that this sum here is this lambda times delta t. So the trick here is like you should know like the Taylor function or the Taylor expansion of the exponential function is the sum of lambda t to the n over n factorial. So if you know this, you have to do something like that you can, from this sum, you can take this exponential out to the sum n times this guy, more or less. And since you have an n here, you can like cancel out one of them, and then you start from one, and so there's a lambda uh, like left, and you can do this sum overall, and you obtain that this is lambda t times e to the minus lambda t, and this summatory is uh, e to the lambda t, so they cancel out more or less, and you obtain this. The same for the variance. You can check like more carefully at home. Okay, so the mean grows linearly with the time. So if we plot this guy over time, you can see like the mean has to grow linearly. Let's plot it here with black. The mean grows linearly with time, and the same the variance. Variance has the same value as the mean. Variance and mean are the same. This is like the fundamental property of the Poisson process. So it's so important that in systems biology it's known that if a process has a Fano factor is defined as the variance over the mean. So this guy on over this guy. If the variance is less than one, because for the Poisson process, the variance is over the mean is one because they are the same. If it's less than one, we call it sub-Poissonian. And if it's greater than one, it's called super Poissonian because this Fano factor is greater than one. Okay, here are some examples of different lambdas. Here you have the time instead of x, but this is the idea. You can plot, and you have to be careful that this distribution is not continuous but uh, discrete. Okay, so we can like do some simulations. So the simulation scheme is going to be the same. Okay, so let's next session I can explain this with the normal distribution. It's going to be different. But for this case, for uh, logarithmic distributed times is or exponential distributed times is fine. Okay, so we define the same function evolve. Our first reaction is going to be this. If our time to reaction is greater than Tmax, we do nothing. Otherwise, we do the reactions. So the reactions are going to be simply S is going to be S plus 1. And that's it. We do this every time for all the reactions until we have Tmax, that the time is greater than Tmax. And we can do this again. Do this for one cell. And if we see the data, you have this is 1,000. So for one cell, you have the name of the cell, 0, the time, and the state 0. So you can plot the states like this. This is an example of trajectory. We expect more or less, because lambda here is 10, the rate of, or we can compare with like the expected mean over time. The mean over time, as I explained you, is simply lambda times 10. So I can plot the time and lambda times t times the time. So this is like the mean is the orange, and the particular trajectory is the blue one. We can do this for different trajectories. Let's say 10. So we simulate this for 10. We see the data frame is 0 to 10, and each of them having different states. And we can like plot each of them. How do we do it? So we can do a for loop for the f for cell in the f cells dot cell dot unique. You have the f cell, let's say, equal to this data frame, such as the cell is cell. So again, let's say we want the data frame with cell 7. So you have all the data for the cell 7. And we plot all of them, and then we can plot this in black. So for doing this, I simply use the color K. That means black. Okay, so you have different trajectories here. Sorry, so this has to be the F cell. That is the name of this data frame for each cell. Okay, so this is the different trajectories with different cells. The mean is follows the function lambda delta lambda t, and let's see the variance, no? Or let's see overall the moments. So we have here the same, no? I think it's the same script. Okay, so we have here now the mean over time and the variance. This is like calculated from the trajectories, but in this case, I won't use only 10, but 1,000. So let's do this again. Why? Because with the more cells we have, the more accurate is the mean. So we do this for 1,000, and we calculate this for 2,000 cells. If everything is fine, shouldn't take much time. It did. Okay. Uh, let's do with 100. How many cells did we have? 13. We can do this. For watch the progress over time, we can use the function QDM. Uh, if- and in this for we can put TQDM inside the range to check the progress over time. So this takes 2 minutes to do 100. Okay, what's this data frame here? What's the problem? We can go 1,000. And we save the data frame later. So again, you have 1,000 cells with the state. But here I change a little bit. Lambda now is 1. You can come back and use 10. And we are uh, calculating here the mean and the variance over time. And we can plot the time and the mean state. And we can compare the mean with the uh, expected mean. No, it's also linear. Yeah, they are essentially the same, and the variance has to grow the same, no, linearly. So here the column of variance is called bar. So as you see here, like the fluctuations of the variance is higher because it's a second order moment. But overall, like the trend is very similar to lambda times t. Okay. Finally, what I wanted to calculate is the problem of the first Pasha time. So what's the idea? The idea is like given different trajectories, I'm not interested only in the distribution of like states at a given time, but also I want to study the time that it takes for reaching a given target. For instance, in this case, 15. Yeah, so this is also important in other kind of research. For instance, calculating the time to division of cells, the time of lysis. For instance, you are studying lysis on other kind of processes that where the time is also stochastic. So what do we do here? So here for the Poisson process, we had started with like an infinite number of states, but now what to do is like our uh, system or our chain, we crop the chain in our state n, such as the uh, evolution ends in state n. So we have, and everything is going to be the same. So P0 has this evolution, P1 has this other evolution, and overall the state n-1 is going to have the incoming flux from n-2 and the outgoing flux to n with a intensity of lambda times Pn-1. Okay, and the last one has only incoming flux from n-1 with this value, lambda times the probability of n-1. So this kind of state that only have incoming flux and not outgoing flux is called the absorbent state, because all the probabilities are in time going to infinite. The probability of this state is going to be 1 because all the flux are going to come to this state. So for estimating this first pass and time statistics, we always make our state of interest as an absorbent state. Okay, in this case, we're interested on how much time do you spend on reaching n steps. Okay, so we can do here like some maths. So until here, the process is Poisson. So this guy follows Poisson statistics. You know already the solution for Pn-1. That is this guy, no? But evaluated in n-1. Okay, so you know here that Pn-1 is Poisson process of n-1. Lambda n lambda t to the n-1 times e to the minus lambda t over n-1 factorial. So this derivative, remember that the distribution is the derivative of the state, as we explained in the previous session. So the the distribution is the derivative of this Pn times lambda. Sorry, it's the derivative that is Pn-1 times lambda. So we just multiply this by lambda and we obtain this guy. Okay, so here you have lambda to the n instead of lambda to the n-1. And this distribution is called Erlang distribution. And you can show that, as I explained here, uh, this Erlang distribution corresponds to consecutive convolutions of exponentials. So if the exponential, I convolve this exponential with another exponential, and then another exponential, other exponential, other exponential, other exponential. And this result is this distribution is the result of convolving different exponential distribution. Remember that exponential distribution has this value, no? Lambda times e to the minus lambda t. So that's where this lambda, the additional lambda comes from. Yeah, and we can like the integral here, now this variable is not n, but the variable is t. So for calculating the mean, I have to do the integral of this distribution over time from 0 to infinite. Yes, so this integral used the definition of gamma function or the function gamma. So it's a little more tricky. You can do it at home more carefully. It's like looking for the definition of the lambda of the gamma distribution, and then you can show that the mean is n over lambda and the variance is n over lambda square. So we can do the same. Estimate the 1,000 Poisson processes and compare it with this distribution. Okay, so what I do here is to simulate not until Tmax, but until I reach the state. Okay, so let's say we want the time on reaching 50. Okay, so while S is less than 50, we do the evolution, and in the end, we save the time. More or less, this is like the idea. We can do this TT even smaller, like for having higher accuracy. Mm, and watch the output, no? So in this case, you have the first column is going to be the cell, and T is going to be the time. So these are the times, but if you want to watch them, like to study them more visually, we can take all the trajectories as well. Okay, now you have the trajectories. No, but I have to save the state, sorry. I forgot. So I forgot to put or to save the state, to start the state. And now you have at a given time and a given cell, the state. So we can plot some trajectories. Oh, here. And let's plot the first 10. Okay, so as you can see here, the uh, simulation stops when we have reached uh, 500. So I wanted 50 now. Sorry. Now with 50. Okay. And we are interested on this time again. So let's do this for 1,000. 1,000, yeah, 1,000 is fine. So I'm gonna save only the data or the time when this process finish. So we let it evolve, and then when it finish, I save the time. So I'm not interested anymore on the whole trajectories, but only in the last time of the simulation. And we can plot an histogram of the distribution of times. Okay, I have something like this. We can increase the number of beans. And you have yeah, we can plot the airline distribution. I don't know exactly how to do it. But we can use this. Okay. So we can call, I don't know, airline this function of the import now. And we have to add the arguments. I'm not very sure what lock is means. Let's see this guy. Mm, okay. We can save as Erlang and save the PDF using this. So usually like here, if I'm right, the log corresponds to l- location parameters is actually the mean, and the scale is the standard deviation. Oh, this is very confusing. Let's do with like quickly with gamma. Gamma makes more sense. Mm. No, let's finish here. Really, we're gonna get more confused. I'll send you this script with the solution for the airline distribution, and I'll let you know how to solve this like more carefully. So thank you guys very much for attending this session. See you next time. If you have any question, no. So thank you very much.